Hi friends, welcome to the lecture of linear algebra. In last lecture, we have completed what is an diagonalizable operator and what is a diagonalizable matrix. Today, we are going to new concept which is a triangulable matrix. Now we have to see what is a triangulable operator and after that what is a triangulable matrix. Okay. Let T be a linear operator on a finite dimensional vector space V over the field here. Then T is said to be T is said to be triangulable triangulable if there exists a there exists an ordered basis there exists an ordered basis curly B for vector space V such that the matrix of T such that the matrix of T with respect to ordered basis curly B is a triangular matrix. Okay, if suppose T be any linear operator which is defined on a finite dimensional vector space V over the field here, then this T is said to be a triangulable operator if there exists an ordered basis curly B for vector space V such that the matrix of linear operator T with respect to basis V is a triangular matrix. Then we say that the given linear operator T is a triangulable operator. Similarly, now we have to see what is a triangulable matrix. Okay. Now a square matrix A of a square matrix A of order n is said to be triangular matrix triangular if there exists a non-singular matrix P non-singular matrix P such that P inverse AP is equal to B where B is a triangular matrix and diagonal entries of entry B are the characteristic values of A. So, what is a triangulable matrix? A square matrix A of order n is said to be triangulable. That is triangular matrix. If there exists a non-singular matrix P, non-singular means it is invertible. That is, there exists a non-singular matrix P such that P inverse AP is equal to B, where this B is nothing but triangular matrix, and the diagonal entries of this B are nothing but the characteristic values of the matrix A. Then we say that the matrix A is triangulable matrix whose characteristic values are the diagonal elements of the matrix B. Okay, now we have to see one theorem. Let V be a n-dimensional vector space over the field here, and let T be a linear operator on V. Linear operator on. Then P is triangulable if and only if the minimal polynomial for T is a product of linear polynomials that is factors over field. Okay. Now, given that V be an n-dimensional vector space over the field here and P be a linear operator which is defined out of an n-dimensional vector space V, then we have to prove that the linear operator P is triangulable if and only the minimal polynomial Mx or T is a product of linear polynomials, that is product of linear factors over the field. Yeah, that is Mx has form. Mx is nothing but something x minus c1 to the power r1, x minus c2 to the power r2, up to so on x minus ck to the power r. That is, if T is triangulable, then we have to prove that if the minimal polynomial for T has this form. Okay, now let us see proof. Given that T be a linear operator on n-dimensional vector space V over the field here. Now we have to prove that T is triangulable if and only if the here the minimal polynomial for T is a product of linear polynomial, that is factors over the field here. Now first assume that the minimal polynomial for P is a product of linear polynomials over here. That is, minimal polynomial has the form Mx is nothing but x minus c1 to the power r1, x minus c2 to the power r2, up to so on, x minus ck to the power r. Now we have to prove that P is triangulable. Okay. Now let W equal to singleton 0 is a subspace of vector space V. Since every vector space has a 0 subspace always. Okay, so W equal to singleton 0 is the subspace of a vector space V, and we know that singleton 0 is always invariant under the linear operator. Therefore, this W is, which implies W is proper invariant subspace of linear operator T, as it is a proper invariant subspace of T. In first chapter we have proved one result, that is if T be a linear operator defined on a finite dimensional vector space V over the field here such that the minimal polynomial for T is a product of linear factors, that is P of x is nothing but x minus c1 to the power r1 into x minus c2 to the power r2 up to so on x minus ck to the power rk, and W is a proper invariant subspace of T, then there exists one vector alpha belonging to V such that alpha is not in W but T minus Ci of alpha is belongs to W. So here W is a proper invariant subspace of T, V be a finite n-dimensional vector space over the field F, and T be a linear operator on V, and the minimal polynomial for T is a product of linear factors. Therefore from this we conclude that there exists a vector from previous theorem, that is the theorem in last chapter, that is previous theorem, there exists a vector alpha 1 belonging to V such that alpha 1 is not belongs to W and T minus Ci of alpha 1 is belonging to W for some characteristic value, Ci of linear operator T. Okay, now here T minus Ci of alpha 1 is belonging to W, and W is nothing but zero subspace, that is W contains there is only one variable, it is a zero element. Therefore as T minus Ci of alpha 1 is belonging to this zero subspace, then this vector must be equal to 0, that is which implies T minus Ci of alpha 1 is equal to 0 since it is belonging to W and W contains only one element which is the 0 element. Therefore this value must be equal to 0, which implies T of alpha 1 is equal to Ci of alpha 1, that is which is equal to A11 of alpha 1, since Ci is equal to A11, that is put Ci equal to A11. Now construct one set, that is space, let W1 be a subspace spanned by a non-zero vector alpha 1, spanned by a vector alpha 1. Then this W1 contains the elements of the tiles which implies W1 is nothing but it contains all vector alpha belonging to V such that this any vector alpha can be expressed as A into alpha 1 since W1 is spanned by alpha 1. Therefore, where A is belonging to field here, that is W1 be a subspace of vector space V which is spanned by alpha 1. As here there is only one vector, that is W1 is spanned by only one vector, and dimension of V will be equal to here. W1 is a subspace of vector space V which is spanned by alpha 1, and dimension of W is not equal to dimension of W1, which implies W1 is a proper subspace of V. Now we have to check whether this W1 is invariant under T. If we take T image of any vector belonging to this W1, then it is again in W. Since if suppose we take T of alpha, then it is nothing but A into T of alpha 1. Okay, and T of alpha 1 is nothing but A11 of alpha 1. That is again it is A into A11 of alpha 1. But this one is the scalar into alpha 1, and W1 is spanned by alpha 1. Therefore, this vector is again belonging to W1. Therefore, by the definition of invariant subspace, this W1 is a invariant subspace of V, and already it is proper subspace, which implies W1 is a proper invariant subspace of T. Okay, invariant subspace of T. Now here again, T be a linear operator which is defined on a n-dimensional vector space V over the field over the field here such that the minimal polynomial for t is a product of linear factors, and here there is one subspace w1 of a vector space v which is invariant under t. Then by again that previous theorem, there exists a vector alpha 2 which is belonging to v such that alpha 2 is not in w1 and t minus ci of alpha 2 is belonging to w1 for some characteristic value, for some characteristic value ci of linear operator t. So t minus ci or alpha 2 is belonging to w, and w contains w1 is a subspace which is spanned by alpha 1, and the elements in w1 are of the type a to alpha 1, so which implies t minus ci of alpha 2 is of the form a into alpha 1, okay, which is nothing but t of alpha 2 minus ci of ci into alpha 2 which is equal to a into alpha 1, which implies t of alpha 2 is equal to a alpha 1 plus ci of alpha 2, which is nothing but a12 of alpha 1 plus a22 of alpha 2. Since put a equal to a12 and ci is equal to okay. Now so here t of alpha 2 is nothing but a1 to alpha 1 plus a2 to alpha 2. Now construct one subspace let w2 be a subspace of v spanned by alpha 1 and alpha 2, which implies w2 is actually nothing but it contains all gamma belonging to v such that each gamma can be expressed as a alpha 1 plus b alpha 2 whenever a comma b belonging to field here. Therefore, here W2 be a subspace of vector space V such that each gamma belonging to V can be expressed as a alpha 1 plus b alpha 2 since it is spanned by two vectors alpha 1 and alpha 2. Now again, here W2 is a subspace of vector space V which is spanned by alpha 1 and alpha 2. Now we have to check whether it is invariant under T or not. If we type any element belonging to this W2 gamma, then it is of the form A alpha 1 plus B alpha 2, and T image of this one is again belonging to W2 itself. Then from the definition of invariant subspace, W2 is invariant under T. Now W2 is a subspace which is spanned by only two vectors already, and here we don't know that whether these alpha 1 and alpha 2 are linearly independent or not. If they are linearly independent, then its dimension is 2, otherwise it is less equal by 2. But dimension of V is n, so 2 is not equal to n. Therefore W2 is a proper subspace of V, which implies W2 is a proper subspace of V which is invariant under T, which is invariant under linear operator T. Then by again that previous theorem, that is from theorem from the first chapter, there exists a vector alpha 3 belonging to V such that alpha 3 is not belonging to W2 and T minus Ci of alpha 3 is belonging to W for some characteristic value Ci of T. Characteristic value Ci of linear operator T. Now as T minus Cii of alpha 3 is belonging to W2, and W2 contains the elements of the form A alpha 1 plus B alpha 2. Therefore, this element has of the form which implies T minus Cii of alpha 3 is equal to A alpha 1 plus B alpha 2. Okay, so which is nothing but T of alpha 3 minus Ci into alpha 3 equal to A alpha 1 plus B alpha 2 plus, sorry, okay, now which is nothing but which implies P of alpha 3 is nothing but A alpha 1 plus B alpha 2 plus Ci of alpha 2. Let us take this one as A13 alpha 1 plus A23 alpha 2 plus A33 alpha 3, since A equal to A13, B equal to A23 and Ci equal to A3. Now, which is true for the W2. Continuing in this way, continuing in this way, we get curly B equal to alpha 1, alpha 2, so on, alpha n of n vectors, okay, where this curly B is an ordered basis for V, since V is a n-dimensional vector space over the field F, where curly B is an ordered basis for V. Now, and each Wi is spanned by I vectors. Since W1 is spanned by alpha 1, that is only one vector. W2 is spanned by two vectors, that is alpha 1 and alpha 2. Similarly, W3 is spanned by three vectors, alpha 1, alpha 2 and alpha 3. Similarly, each Wi is spanned by I vectors, which are alpha 1, alpha 2 up to so on, alpha I. And P of alpha j is nothing but A1j alpha 1 plus A2j alpha 2 plus up to so on plus Ajj alpha j, wherever j is running from 1 to n. That is, any P of alpha j can be written as A1j alpha 1 plus A12j alpha 2 plus up to so on A j alpha j plus 0 into alpha j plus 1 plus up to so on plus 0 into alpha 1, whenever j is running from 1 to n. So now this type of equation has the matrix form. Therefore, the matrix of linear operator 2 with respect to order basis B is given by A equal to matrix of linear operator T with respect to order basis T is given by. First one, W1 contains, there is only one vector which is a A11. A11. And remaining are 0, 0, 1, 0. Now, in second one, A12 and A22. And remaining elements are 0. Third one, A13, A23, A33, and remaining elements are 0. And so on. Last one, A1n, A2n, A3n, and up to so on, AN. Okay. And which is a square matrix of order n cross n. Now, from the definition of triangular matrix, a matrix is said to be a triangular matrix, or an operator T is said to be a triangulable operator if there exists a basis curly B for V such that the matrix of linear operator T with respect to basis B is a triangular matrix, and here the given matrix is a triangular matrix. Okay, as it is a triangular matrix, then we say that the linear operator T is a triangulable, which implies P is triangular. Okay, so here we have proved that if the minimal polynomial for linear operator T has a product, if the minimal polynomial for a linear operator T is expressed as a product of linear factors, then the linear operator T is triangulable. Now in second part we have to prove that if T is triangulable, then it can be then its minimal polynomial can be expressed as a product of linear factors. Now conversely, assume that T is triangulable. Okay. As T is triangulable, which implies there exists an ordered basis curly B for V such that the matrix of linear operator T with respect to basis curly B is a triangular matrix. Let us suppose this matrix is A. That triangular matrix will be A. Then it has of the form this form. Okay. So which is of the form this one. And we know that the characteristic polynomial of P is given by determinant of xi minus A. And in previous lecture we have proved that the matrix of linear operator T with respect to basis B is of this form. Then its a characteristic polynomial f of x is given by fx is given by x minus c1 to the power r1, x minus c2 to the power r2, so on, x minus c8 to the power r2. Actually, we can find out from previous theorem or here as we use the triangulable matrix, then find determinant of xi minus i. Xi is nothing but x into I1 0 x into I2 0 is a square matrix of order n cross n. Since here we know that the diagonal elements of the triangulable matrix are nothing but the characteristic values of the matrix A. So here each characteristic values may be repeated some certain number of times. Therefore, from this we can find out determinant of xi minus c minus A. A is nothing but c1 into I1. Here we don't know whether the diagonal elements of this matrix are distinct or not. So here there is a possibility that each eigenvalue can be repeated certain number of times. Therefore, it is nothing but c1 I1 0 up to so on 0, 0, c2 I2 up to so on 0, and so on 0, 0, ck I2. Okay, so which is also n cross n matrix. So if we find the here there is a determinant. So here we get n cross. Now, if we find out the determinant, then we get the polynomial f of x is equal to here we get these elements a1 to a1, actually they are nothing. Here not here. c1 I1 c2 I2 up to so on ck ik, but these elements are non-zero. That is some a b c whatever it would be. Okay. So you will find out this characteristic polynomial, then f of x is nothing. Okay. If we find out, then we get this minus this, that is x minus c1 into I1, x minus c2 into I2, which is on diagonal elements, and here we get the negative elements. But we know that the characteristic polynomial or the determinant of a triangular matrix is nothing but the product of its diagonal entries. Therefore, whatever will be these values, then they are not in the determinant or in characteristic polynomial. So its characteristic polynomial is nothing but x minus c1 to the power something d1, x minus c2 to the power d2 up to so on, x minus c2 to the power d2. Okay, now this one is the characteristic polynomial. But we know that let us take this one as the equation 1. We know that the characteristic polynomial, the minimal polynomial always divides the characteristic polynomial. Then the minimal polynomial has also the same form. And actually there is one another theorem. The minimal polynomial and characteristic polynomial of the linear operator t has the same root except the multiplicity. Therefore, from these two theorems, the minimal polynomial has the form. The minimal polynomial has the form s minus, that is m of x, is equal to s minus c1 to the power r1, x minus c2 to the power r2 up to so on, x minus ck to the power r, where each I remain from 1 to k is less equal by di, where the I remain from 1 to k. Since the minimal polynomial and characteristic polynomial have the same roots except the multiplicity. Okay, so here is the proof. So here we have proved it is a triangulable operator. Then the minimal polynomial for t is a product of linear factors, that is linear polynomials, and hence the required result. Now we want to see one example on triangulable matrix or triangulable operator. Okay. Let P from R3 over R to R3 over R is a linear operator defined by P of x, y, z is equal to 3x minus y plus j, comma 7x minus 5y plus j, comma 6x minus 6y plus 2j. Okay. Now show that P is triangulable and find the triangular matrix. Okay. So here given that one linear operator which is defined from R3 over R to R3 over R and which is defined by d of x y z is equal to 3x minus y plus z 7x comma 7x minus 5y plus z comma 7x minus 6y plus 2z. Now we have to show that this T is a triangulable operator and we have to find here the corresponding triangular matrix. Okay. Now first we have to find out its matrix, that is matrix of given linear operator. After that we have to find out whether it is a triangular matrix or not. Okay. Now from T, its a matrix is nothing but, suppose A be a matrix, then which is nothing but 3 minus 1 1 7 minus 5 1 6 minus 6. Now we have to find out the characteristic polynomial and minimal polynomial. If the characteristic polynomial find out and its minimal polynomial is the product of linear factors, then from previous theorem we say that directly the T is triangulable. So characteristic polynomial of this operator is given by determinant of a minus xi, and which is nothing but f of x, and which is equal to determinant of a minus xi is nothing but determinant of a 3 minus f minus 1 1 7 minus 5 minus x 1 6 minus 6 2 minus x. This one is the characteristic polynomial, which implies f of x is equal to 3 minus x into minus of 5 plus x into 2 minus x plus 6 plus minus of plus 1 into 7 into 2 minus x minus 6 7 into 2 minus x minus of 6 plus again 1 into 7 into 6 minus of 42 plus minus common minus of 5 plus x minus of minus plus 6 into 5 plus x plus 6 into 5 plus. Okay, so solve this. We get 3 minus x in minus as it is 5 into 3 minus of 5x plus 2x minus of 3x minus of x square into plus 6 plus 7 into 14 minus 7x minus this 6 plus minus of 42 plus 30 plus 6x. Okay. Now which is equal to 3 minus x into x multiply inside by minus x minus sign, we get x square minus of minus plus 3x minus of 10 plus 6 minus 4 plus 14 minus 6 minus 8 plus 30, sorry 14 minus 6 8 8 plus 30 38 38 minus 42 minus of 4 minus of 7x plus 6x minus 6, so which is equal to 3x square plus 9x 3x square plus 9x minus of 12 minus x cubed minus 3x square plus 4x minus 4 minus of x, which is equal to 3x square cancel minus of x cubed 9x plus x 9x plus 4x 13x minus 6 12x minus of 12 minus of 4 minus of 60. Okay, so this one is the characteristic polynomial. Now we have to find out its characteristic equation. Characteristic equation means nothing but characteristic polynomial will be equal to 0, that is fx will be equal to 0, which implies f minus of x cubed plus 12x minus 16 is equal to 0, which is nothing but x cube minus 12x plus 16, which is equal to 0. Now we have to find out the roots of this polynomial. So if we put 1 then 1 minus 12 plus 16, which is not equal to 0. But we put 2 cube is 8 minus 12 into 2, 24 plus 16 is equal to 0. 8 plus 16, 24 minus 24, which is equal to 0. Then by synthetic division method, which is nothing but x cube 1, there is no term of x square, which is 0, minus 12 plus 16. Now 1 as it is, first root is 2. 1 into 2, 2 plus 0, 2. 2 into 2, 4, minus 12 plus 4, minus 8. Minus 8 into 2, minus 16, which is 0. So here, x minus 2 into x square plus 2x minus 8 is equal to 0. Now we have to find out two values whose sum is 2 and product is minus 8. Let us say 4 and minus 2. If we take 4 and minus 2, then 4 minus 2 is 2 and 4 into minus 2 is minus 8, which is nothing but x minus 2 into x plus 4 into x minus 2. X minus 2 is equal to 0, and which is nothing but x plus 4 into x minus 2 square is equal to 0. Therefore, its characteristic values are equal to minus 4 and 2, 2. Now, this one is the characteristic equation. That is characteristic equation. Then its minimal polynomial is given. If we find out its minimal polynomial, then its minimal polynomial is same as its characteristic polynomial. Polynomial is x minus 2 square into x plus 4. But in previous lecture we have proved that if the minimal polynomial of a given linear operator t is expressed as a product of linear factors, then its corresponding linear operator is t is a triangulable. Then by that theorem, t is triangulable. Okay, so here we have proved that t is triangulable, but it remains to prove that it remains to find out its corresponding triangular matrix. For that, we have to find out the eigenspaces corresponding to these eigenvalues minus 4 and 2. So, the eigenspace corresponding to eigenvalue minus 4 is, that is W1, that is nothing but the eigenspace corresponding to eigenvalue minus 4. And which is nothing but the actually the nullity, that is which is eigenspace is nothing but the null space of t minus this t minus minus of 4i, which is t plus 4i. That is, it is nothing but null space of t plus 4i. Okay, that is, it is a collection of its corresponding eigenvectors. So t plus 4i of x will be equal to 0. So which is nothing but null space is nothing but we have to take the mapping which is maps to codomain, the zero value of the codomain. So t plus 4i is nothing but the a plus 4i. A is nothing but matrix A. 3 minus 1 1, 7 minus 5 1, 6 minus 6 and so 3 plus 4 7 minus 1 1. 7 minus 5 plus 4 minus 1 again 1, 6 minus 6, 2 plus 4 is 6. Of this 6 y is equal to 0 0 0, which implies now here r2 minus r1, that is r2 is changing to r2 minus r1 and R3 is changing to R3 minus 6 times of R1, which implies now first row is as it is. Now 7 minus 7 0, minus 1 plus 1 0, 1 minus 1 0, 6 minus 7 into 6 42, 6 minus 42 minus of 36. minus 6 minus of minus 6, which is minus 6 plus 6, which is 0. 6 minus 6, 0 into xyz, which is equal to 0 0 0, and which is nothing but 7x minus of y plus z equal to 0, and minus of 36x is equal to 0, which implies x must be equal to 0. As x equal to 0, then 1 becomes 7x, 7 into 0 minus of y plus z equal to 0, which implies y is nothing but z. So its characteristic space w lambda 1 equal to minus 4, which contains all x, y, z belonging to R3 such that x equal to 0 and y equal to z whenever x, y, z belonging to R. That is its characteristic. It is nothing but x equal to 0 and y whenever y is belonging to R. So this one is the characteristic space associated with the characteristic value minus 4. Similarly, if we find out the characteristic space associated with the characteristic value 2, then here lambda 2 and here null space of t minus 2i, and which is nothing but t minus 2 into I. Again take 3 minus 1 1, 7 minus 5 1, 6 minus 6 2. Now this one is the matrix A, that is A is nothing but, now 3 minus 2 1, 1 minus 1 1, 7 minus 5 minus 2 minus 7, which is 1, 6 minus 6, 2 minus 2, which is 0. Okay, now R2 is changing to R2 minus 7 times R1, and R3 is changing to R3 minus 6 times of R1, which implies 1 minus 1 1, 7 minus 7 0, minus of 7 plus 7 0, 1 minus 7, 1 minus 7 minus 6, 6 minus 6 0, minus 6 plus 6 0, 0 minus 6 minus of 6, and actually minus 6 minus 6 of 6, which is 0 from next of xyz, which is equal to 0 0 0. Actually here we is changing R3 is changing to R3 minus R3, so which is nothing but this one, which implies minus of 6y will be equal to 0, and as minus 6y equal to 0, which implies y is always equal to 0, and x minus y plus z is equal to 0, as here y is plus square, not y equal to 0, here z equal to 6, z equal to 0. Minus of 6z is equal to 0, which implies z equal to 0. As z equal to 0, then x minus y is equal to 0, which implies x equal to y. As x equal to y, then the eigenspace corresponding to eigenvalue 2 is equal to, it contains x is equal to y. Therefore, x comma z is 0 belonging to R3 whenever all x belonging to R. Therefore, these are the characteristic spaces associated with the characteristic values minus 4 and 2. Okay. Now, here we have to find out one third vector, which is linearly independent. Since here R3 over R, then its dimension is 3. So here we have to find out the third linearly independent vector. So let 0 1 1 1 is characteristic vector associated with characteristic value minus 4, and 110 is a characteristic vector associated with characteristic value 2. Okay. Now we have to find out the third vector. Let alpha equal to 1, 1, 1. Now the elements of eigenspace corresponding to eigenvalue lambda 2 is nothing but x x 0. That is here the elements of the type 1 1 0, 2 2 0, 3 3 0. Here 1 1 1 1 is not a member of W, that is eigenspace W lambda 2. Is not belonging to W lambda 2. So in previous lecture we have proved that if alpha is not a member of W lambda 2 and it is invariant under T, then which implies there exists a polynomial g of x is equal to x minus 2 such that this g of T of alpha is belonging to this W lambda, which is from previous theorem. That is T minus this alpha I, sorry, T minus Ci of alpha is belonging to this W lambda. Okay, now T of alpha is nothing but 1 1 1 minus T minus here actually we are taking 2, so characteristic value is 2. So 2 into I of alpha is nothing but element itself, which is 1 1 1 is equal to, which is belonging to W lambda 2. W lambda 2 contains the elements of the type 1 1 0 2 2 0. Therefore it is equal to 1 1 0. So which is nothing but T of 1 1 1 is equal to 1 1 0 plus 2 into 1 1 1. Okay, so T of 1 1 is nothing but 1 plus 2 3, 1 plus 2 3, and which is okay. Now here we get one vector 1 1 1. So here we find out one basis curly b, or one set curly b equal to, first element is 0 1 1, second one is 1 1 0, and third one is 1 1 1, and which is the basis for your given domain, that is R3 over R. Okay, now let x1 will be equal to 0 1 1. Now x1 equal to 0 1 1, then T of x1 is equal to, now we given that T of xyz is nothing but, we know that T of xyz from given definition, T of xyz is equal to 3x minus y plus z, comma 7x minus 5y plus z, comma 6x minus 6y plus 2z. So T of x1 is T of 0 1 1, which is equal to, put x equal to 0, y equal to 1, and z equal to 1. As x equal to 0, 3 into 0 0, minus 1 plus 1, which is 0. Okay, now 0 minus 5 plus 1 minus 1. Okay, now 6 0 minus 6 plus 2, again minus 4. Now we have to write the 0 minus 4 minus 4 as a linear combination of these three elements. So which is nothing but minus of 4 into 0 1 1 plus 0 into 1 1 0 plus 0 into 1 1 1. Okay? 0 minus 1 or minus 4 can be written as a linear combination of these three elements, which is nothing but minus of 4 into 0 1 1 plus 0 into 1 1 0. Actually these values are gives 0 value, and minus of 4 into 0 0, minus 4 into 1 minus 4, minus 1 into 1 minus 4, and which is nothing but this one. Okay, similarly T of x2, which is equal to T of x2 is nothing but 1 1 0. And which is nothing but, now we have to put x equal to y, y equal to 1, x equal to 1, y equal to 1, and z equal to 0. X equal to 1, 3 minus 1, 2. Again, 7 minus 5, 7 minus 5, 2, which is 0. 1 1, 6 minus 6 0, actually z is already 0, which is nothing but 0. Now we have to write this one as a linear combination of these three elements, and which is nothing but 0 into 0 1 1 plus 2 into 1 1 0 plus 0 into 1 1 1. So this one is the first one, this one is second one, and P of x is equal to P of 1 1 1. And already we have found out P of 1 1, which is nothing but 3 comma 2 comma 2. This one is the third, and this third one can be written as 0 into 0 1 1 plus 1 into 1 1 0 plus 2 into 1 1 1. Okay, this one. Now we have to write the matrix of linear operator T with respect to ordered basis this B, which contains three elements. Therefore, the matrix of linear operator T, which is denoted by A, matrix of linear operator T with respect to this B is nothing but first one minus 4 0 0. Here we have to take coefficient of this linearly independent elements, which are minus 4 0 0. So write this one into 1 minus 4 0 0. Second 0 2 0. 0 2 0, and last one 0 1 0 1. So this one is the corresponding triangular matrix of a given T. Okay, thank you for watching the lecture.